Yeah, so yesterday we finished off here. We discussed the strategy for this problem, and as I mentioned in class, the strategy is kind of the tough part, because if you can't figure out within a few seconds what you're supposed to do on the problem, it becomes very, very, very tough to finish the problem in time. Okay? This would be a typical problem that is not calculator allowed, because everything in here is totally doable without a calculator. So, I'll briefly go through the derivative and plugging everything in. And don't forget, like, the big part of it was understanding these last couple words, because these define what you're supposed to do and how to do it. So, what's the value of t is a particle speeding up? So we are given a velocity equation. Speeding up implies that the acceleration is positive. Those two pieces are very important to understanding how to approach this problem. Because if I know I need the acceleration, then I just take a derivative of the velocity formula. If I know it means speeding up, that means I need to be bigger than 0, so I can use that to plug in the information. Take a derivative, and then plug in these three numbers. So I'm going to take a derivative real quick. So v prime of t. This will be my acceleration equation. So I'm going to have to use a quotient rule, so I will do that first. Low cosine of 2t, d high, so times the derivative of sine of t, derivative of sine of t would be cosine of t, minus high d low, so high sine t, d low would be 2 sine of 2t using the chain rule. Oh, the square of below, so cosine of 2t quantity squared. Ah, yes, that would turn this into a positive. Okay, so this is actually really helpful because if I plug in these numbers, like some cool things pop out. So first of all, let's all agree the bottom should be positive. You might be tempted at this point to be like, okay, let me show off my cool trig skills. Don't bother. You're going to spend more time trying to remember your Pythagorean identities than you would just plugging it in and trying to simplify this thing. So I'm going to plug in pi over 6. So if I plug in pi over 6, let's talk about what each thing happens. So at pi over 6, I would do cosine of pi over 3 times cosine of pi over 6 plus sine pi over 6 times 2 sine of pi over 3 all over cosine pi over 3 squared. My goal is to see if it's positive. That's all I really care about. Well, cool things. Pi over 3 is in the first quadrant, so all of its values are positive. Pi over 6 in the first quadrant, all of its values are positive. So I get a positive number times a positive number, plus 2 times a positive number times a positive number. So positive, 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 positive. Everything on the top is positive, divided by a positive number. The answer is positive. That should work. That's all I have to do. I don't care what the value is. Now, as I get to more extreme values, I may need to check certain pieces to see if it does matter. But in general, like, that's it. That's all I've got to do. Now, for that one, I think I can get away with it. For the next two, because of how they're situated, I may end up having to actually plug them in. This is why I recommend it again. You weren't here, Ricky? So I recommend it to everybody that when you're getting ready to take the AP exam, when you walk through the door, the first thing you need to do is mentally write down your entire cheat sheet and unit circle. Make sure it is 100% perfect. No problems. That's something you can practice the day or two before. Don't bother practicing a bunch of extra problems. As we mentioned, it's not something going to be very useful. Instead, get that cheat sheet down because you've done these problems before. If you can just get that first step, at least 80% of the problems you should have a good shot on. Okay, so get that cheat sheet memorized, practice writing it down, get used to it, get used to your hand, having the ability to write it out. And then do the same thing with the unit circle, and then check it to make sure you did it right. If there's anything wrong, don't just do it again. Correct it, keep practicing. Okay? So now I plug in pi over 3 and 2 pi over 3. I plug in pi over 3. Let's see. I plug in pi over 3, so I'm going to do an acceleration of pi over 3. It's equal to cosine of 2 pi over 3 times cosine of pi over 3 plus sine pi over 3 times 2 times sine 2 pi over 3 all over cosine of 2 pi over 3 squared. So I'll use my unit circle to check this. Cosine of 2 pi over 3. That would put this in the second quadrant. In the second quadrant, cosine is negative, so it's possible this first term is negative. Times a positive, so a negative times a positive would make this piece a negative number, plus sine of pi over 3 and times 2 sine of 2 pi over 3. Positive number because it's in the first quadrant, positive number because it's in the second quadrant, times 2, so I have a positive number and a negative number being combined together, and the bottom should be positive. This one is a maybe. I need to plug in the unit circle. Because it's entirely plausible that when I plug this thing in, it does in fact produce a negative value. Guess what? So it worked. So yeah, at that point I stop and I'm like, hey, which is impossible? B. Well, impossible. The reason being, when you plug in the third one, because of the doubling, 2 pi over 3 goes to 4 pi over 3, and 4 pi over 3 puts it into a third quadrant where everything becomes negative. And so a lot more pieces can become negative. That makes this bottom piece become negative. Negative 5. Perfect. So as you can see, like this is kind of how you have to approach it. Okay. I don't need the exact value. I just want to make sure it matches what I want it to do. And there are a lot of ones that are like this that end up being like you don't actually need to find the full solution. You need to make sure you know what it looks like. There is a difference that you can tell though. The ones that have these like 1, 2, and 3, those are usually ones where like you don't actually have to plug everything in. Okay. Question to number 7. Okay, I want to prioritize because I know we're gonna have senior skip day on Friday, and on Thursday we're gonna not be here. So
they're gonna call it cops or bring cops to your house if you skip.
That's what they said.
What?
good.
What is it?
I don't think that they. I'm like, of course.
1.
So stupid. I'm just using my phone there.
So this time, a particle starts at time t equals 0 and moves along a number line. So its position at time t greater than or equal to 0 is given by x of t is equal to t minus 2 cubed times t minus 6. Which of the following intervals is a particle always moving to the right? So let's analyze this particular problem. We are given the position equation, so that's x of t, and it asks us on which of the following intervals is the particle always moving to the right. So what's positive? I'm sorry, I didn't hear that.
Positive velocity.
Positive velocity. So I need the velocity equation, and I need to see when it's positive. Yes. That's my 2 pieces. So what should I do if I want to do that problem?
Derive.
Take a derivative. And then?
And see where's plus 0.
No.
Second.
You have the right idea. But save yourself some headaches. Okay? What you want to do is test the 4 answers. Okay? So what I would look at this and say, okay, which one only gets me one of the answers? If I plug in 1, the only answer is A. Okay? Or like D. So what I want to do is I want to pick some values where I can start to test to see if any of these are true or are not true. So when I look at this list, I look here and say, hey, I can use 1 to test this one and that one. I can use 3 to test this one, and that's it. And I can use 6 to test this one. And then if I run out of options, like, it's going to be never. Look at this and say, okay, I might start by testing 6. If I plug in 6 and the answer is positive, well, then the answer has to be C. I'm done. Or it has to be D. I'm done. Like, just use the answers to try to help guide you on what you should be doing. Because, yeah, you could just do the first fundamental theorem of calculus, right? So the first derivative test. You could do that in this problem and find the answer and then make sure it matches one of these. Or you can use the answers you have. Both work, but one's going to be faster than the other. Now, this problem is a changeable problem. with a product inside of it. So let's go ahead and do the derivative real quick so we can get to practice. As a reminder, I have t minus 2 cubed times t minus 6. I'm going to take the derivative. So I could, if I wanted to, boil this big thing out. Okay then. Let's do it. I would do left d right. So left t minus 2 cubed d right. The derivative of t minus 6 is 1. Plus right d left. So t minus 6 times the derivative of the left piece. The derivative of the left piece has a power, so I do the power rule first. Subtract 1 from the power, and then I multiply by the derivative of the inside. The derivative of the inside is 1. Do not neglect that last piece. I'll simplify what I can, but otherwise I'm going to just leave it where it is. This becomes t minus 2 cubed plus 3 t minus 2 squared times t minus 6. Right?
Oh, yeah, sorry, I didn't see your addition sign.
Okay, so there's my derivative. So now I can take those numbers I picked out and see if any of them work. So like I tried 1. 1 minus 2, that's going to be a negative number. It's going to be cubed. A negative cubed is going to be still negative. Plus 1 minus 2 squared, that's going to be a positive. 1 minus 6 is going to be a negative. I get a negative 5 times a positive number times 3. This thing's going to be really big and negative. This thing's going to be negative. I get a negative answer at 1. At 1, I am negative. So what answers does that eliminate? A's out. D's out. Now I'm down to 3 possibilities, right? So now I pick another number. Let's try, I don't want to pick 2 because it won't test B. Now I could test 4 to just test B. I could test 6 to just test C. And if I test both of them and they don't work, the answer is E. So I'm going to try 4 first. So I'm looking 4. 4 minus 2, that's going to be 2. 2 cubed is 8. So I'm trying 2 now. So I get 8 plus 4 minus 2, that'd be 2. 2 squared is 4, times 3 is 12. 2 minus 4, that'd be negative 4. 12 times negative 4 is negative 48, so negative 48. And positive 8, that's going to be negative. So the answer is either C or E. I tried filling in 6.
Positive.
The nice thing about 6 is, yeah, this becomes 0. And this is positive. So it's got to be C.
Already.
Use your answers to help you, right? These are the only things that are possible, right? So use them to help you. Just be careful. If you're going to do that, you have to be willing to take the time to be like, okay, if 1 is negative, what does it eliminate? And make sure you don't just mark it out before you realize, oh, I did that wrong. Because you don't want to mark out the right answer. Okay. Interesting. What would be my alternatives? Ooh.
You could put, well, this is not a graphic portion.
You could graph it. If I graph it, what would I look for?
Where it's positive.
Where what's positive?
Slope.
Slope is positive. So that'd be option B. If this was a graphing problem, that's probably what I would do. Let's be honest here.
It's not calculated though.
It's probably not in this case. But if it was, like, look for those opportunities. Alright? So, answer C. Number 2. The sine graphs for the velocity v of t and the acceleration a of t of a particle moving along the x-axis for t greater than 0 are pictured to the right. On which intervals of time is the speed of the particle decreasing? So, what does that mean? What does it mean when it says the speed of the particle is decreasing? The acceleration is negative. So, where does that happen? So my answer is 1. Okay. So I agree 1. 3 and 5 are also places where this particle is slowing down, right? Because it still has a negative acceleration, right?
But there's no out 1 for 1, 3, and 5.
So of those ones, which one's the best option?
1 or E.
Why would you think they might have not included the other two?
Just trying to trick you up.
Yeah, that'd be a good option, right? It could also be that it's not like which intervals it actually covers the entire thing. And so, like, you want to look at it and be like, hey, if I have more than one solution, like, is that actually what I'm supposed to get, or is that, could they be trying to trick me? So, yeah.
That's weird that they do that and then do.
But look at this question. Like, if you understand it, it's a 10-second question. If you don't understand it, you're going to look at this and be like, where's the equation?
I'm not gonna lie, I looked at them and I was
Okay. Whew. I think these last two multiple choice, not three. I have much multiple choice. Sweet. All right. Yeah. The graph of the velocity b of t in feet per second of a car traveling on a straight road for 0 to 50 is shown to the right. On which of the following intervals is the acceleration of the car negative? What do you guys think?
So you take a derivative, so you want to see their slopes.
Good. So I'm looking for a derivative. I'm looking for when my slope is negative. Those are the same things, right? So in my picture of these three, so 2, so the answer is C. So even if you're not sure what to do in this problem, like there's two answers that pop out because two of them have similar properties. Okay? 0 to 10 has a positive slope. 50 to 35 has a positive slope. So like they at least have the same property. Even if I had no idea what to do though, I might notice that like, hey, positive slope for 1, positive slope for 3, but there are other places that have positive slopes too. So like it's kind of hard to justify why 1 or 3, even if I ignore this entire problem. If I hide the instructions and I just look at the three answers, it's hard to accept that the answer is not 2. Because 2 is the only thing where something unique is happening that's not happening anywhere else in the graph. Okay? 7. Notice that a lot of these are not a lot of math. They're a lot of understanding the problem. And understanding the connection and how it fits together. Knowing that if I have velocity, I need acceleration. That just means I'm talking about slope. That kind of stuff is not like, oh, let me pull out a formula and do this. I have to understand the concept. And that tends to be what throws people off on the AP exam is because there are the ones that will test your physical skill. There are ones that will test your conceptual skill. And most people are good at one and not the other. Like you're either really good at formulas, but you struggle with understanding the concepts, like as a general picture. And something like, I understand what they're talking about, I just sometimes make mistakes with formulas. And like, you will find that these kinds of problems, like you just kind of have to pick a poison, work through the ones quickly that you can do well, and give yourself as much time as possible on the ones that are the harder ones for you, so you can try to get them right. 7. A particle moves along a straight line. The graph of the particle's position, x of t, at the time t is shown above for 0 to 6 seconds. The graph has horizontal tangents at 1 and 5 and a point of inflection at t equals 2. For what values of t is the velocity of the particle increasing?
What's the second derivative?
So yes, we're given the position function. It's asking how the velocity is increasing. So velocity is the first derivative. Acceleration is the second derivative. If it's asking how the velocity is increasing, it's asking about acceleration. This statement implies acceleration. Now I'm given x of t. So that means I'm looking at a second derivative. So what does it mean if the velocity is increasing? What's that going to tell me about the second derivative? And so I'm looking for a place where the second derivative is positive.
We have a point of inflection at 2, so it's defined left or right.
So either we're looking at this piece or that piece. But what does it mean in terms of a picture for the second derivative to be positive? There's a word for it.
Positive y.
Can
So let me get to yours. What were you saying?
you automatically put that because it's not starting at 2, it's just
If you remember that it's dealing with the second derivative, yeah, I would. Boom, gone. Probably also the same thing for D and E, right? Because if I remember that's the second derivative, then I want pieces that deal with the second derivative, which are points of inflection, right? So 2 is the one that matters. So notice that this splits it into 0 to 2, this piece, and 2 to 6, that piece. So back in chapter 2, we talked about the second derivative test. It dealt with something called concavity.
Positive concavity.
What does positive indicate?
It's facing up.
It's opening upwards. It's a U. What does negative indicate?
It's facing down.
Facing downwards. It's an N.
So enthusiastic.
So it's
So
N.
enthusiastic. So we've now recognized that we're dealing with the second derivative, which means we have to look at the point of inflection. With the second derivative, we're now determining that we want it to be positive, which means we need to be concave up. So which of these answers is correct?
Hey.
Sorry.
Hey.
Again, minimal math, but great understanding that you have to do it. Okay, this is one of those problems that if you don't understand the topic and can just do power rules, like, you will never get this question. Except by chance.
How do you know that you have to take a second derivative?
Because it mentions the change to a velocity. It says the velocity is increasing. That means the velocity is changing, and if velocity is changing, that's called acceleration. If it mentioned the change of the slope, that's the same thing. In the second derivative. Remember, each derivative is a change. So if it says the velocity is changing, that means I need a derivative of velocity.
Oh, because the derivative of position is velocity. Okay.
And then jerk.
Then jerk.
That's right.
Doesn't matter. Jerk doesn't matter.
What?
Jerk doesn't matter is what she said.
Correct.
I'm trying to keep them in the position, velocity, acceleration.
Okay. The maximum acceleration attained on the interval 0 to 3 by the particle whose velocity is given by v of t is. So the first step I need to understand is, what am I going to do?
Right.
What?
Because you want to get to your acceleration.
Specifically, why do I want to get to the acceleration?
Changing velocity.
That's right. So then I go to the next phase. Once I take the derivative, that's great to know that's what I'm supposed to do, but what do I do next?
Plug in your answers.
And see what?
See which ones are the highest.
Perfect. Perfect. Much better. Alternatively, the correct mathematical approach would be to take the second derivative, set it equal to 0, and find your points of inflection and all that stuff, and see which ones possibly match, and then try to do it. But no, they've given us the possible answers. Take the derivative, find the acceleration, and then plug these in to the derivative to find the maximum acceleration. So for this problem, let's go ahead and walk through it. Take that derivative for me. It's a pretty easy derivative.
3t squared minus 6t plus 1. Plus c.
No! Don't be that guy. Okay, if I'm doing this by hand without a calculator, I probably factor this to make it a little easier to work through. Because it actually does get easier if you factor it. If you ever had to do mental math, like this is a shortcut you can try, watch. This becomes 3, t squared minus 2t plus 4. And this is actually easier to do than the original. Like if I plug in 9 squared is 81, minus 2 times 9, that's 18, 81 minus 18, that would be 63. Plus 4, that'd be 67 times 3. You end up with 204.
Yeah.
So that's pretty big. Now I plug in 12. Do the same thing. Now I plug in 14. Do the same thing. Like, I think that'd be a reasonable approach.
Let's do 49 squared, yes.
49 squared, so 50 squared would be 2,500.
Yeah.
49 squared would be 49 times 1, 49 times 50.
Assuming the black guys, look at it go.
2,331. Oh, my brain. Oh, God. Oh, part vessel. Please tell me I'm wrong.
You're wrong.
Okay, good. My brain was going to fry at that point. Never again. Oh. That actually hurt. How close was that? Pretty close.
124 or 1.
I was only 70 off. That's small. But I'm gonna guess that E's probably my answer. Like,
Yeah.
that's 49 squared is gonna be really big. If I subtract something off of it that's not very big, like it's probably gonna stay big, and then times number 3, like it's probably reasonable.
Wait.
See that? Make sure I pass it.
Interpret the question.
Oh.
Because it's on the interval from 0 to 3. So wouldn't we have to plug in like 0 through 3 to see which of those answers?
That's what I was
Ooh. Make sure you look at your problem.
I'm glad that I was thinking the same thing, but then you guys continued, and I was like, okay, we'll go with that, I guess.
Okay, so if I want to test this on this specific interval, I need to test 2 things: the endpoints and any values that are critical in between these. So any place where this could be 0. So let's start by plugging in 0 and 3. So 0, I get 12. So that's looking good. And that also eliminates A as an answer, by the way, because it's not possible for 12 to be an answer and 9 also be an answer. I plug in 3. 3 squared is 9, minus 2 times 3 is 6. 9 minus 6 is 3, plus 4, that is 7. 7 times 3 is 21. So that eliminates B as an answer. And C as an answer. So it's either D or E.
Wait, wouldn't it just be, have to be D? Yeah, I should go there.
Ah.
Because the interval is between 0 and 3.
But maybe 2 is bigger. Maybe I plug in 2 and it gets a bigger value.
Or maybe you get 0. Oh, I know you get 12.
The odds of that.
Why not?
It's a quadratic. You should know how it works.
There you go. I know this thing's going to have this shape, right? If I plug in 0, like, where could I possibly be, right? I could be, like, looking at this interval. I could be looking at this interval. I could be looking at this interval. Well, of those options, which ones matches what I just plugged in? The first number I got was 12. The next number I got was bigger. The only times that could happen would be, like, here and here. Well, like, I plug in 1 here, and I plug in, like, 1 there, where, like, I get a lower value followed by a higher value. That's one possibility. Or I do it, like, here and here. That's the other possibility. In either case, nothing in between them is bigger. So like it has to be, I don't know. Right. So knowing how the function looks is also helpful. Now, if I was forced to do this by hand and prove that the other answer is not possible, like I would have to use a quadratic formula and see where my critical value is and test it too. So I come up here. I use a quadratic formula. Do 2 plus or minus the square root of 4 minus 4 times 1 times 4 is to be 16, all over 2a is to be 2. 4 minus 16 would be negative 12. Yeah, that's imagining. So, all right. Next. Oh, I love this one. I love this one. This one's great. Again, it's one of those where like I have very little math to do. I have to understand the concept. So number 3. The graph below shows the distance s of t from a reference point of a particle moving on a number line as a function of time. Which of the following points marked is close to the point where the acceleration first becomes negative. So, important things to point out. This is s of t. Right? S of t. We're looking for where the acceleration is doing something, so we're looking at the second derivative. That implies we're looking at points of inflection. So this can eliminate some answers. Alright? B and D. Both out. Why?
Oh, wait,
No,
they're
because
zeros.
that's for like.
They are first derivatives equal to 0. They are critical values. They are not points of inflection. So they are out. Remember, if we're looking at the acceleration, we're looking at the second derivative. And second derivative cares where we're changing concavity. Now, this leaves us with 3 possibilities: A, C, and E. A, C, and E. What I can look for here is I can look for odd ones out. I could know what that actually implies. Why do you think C? What do you mean they go back the same?
That graph shows they go from positive to negative.
What goes from positive to negative?
ST and E go from positive to negative first. So on the second derivative, they do the same.
I think I know what you're saying, but I think you're just saying it in a weird way. Okay, so let's talk about each of these in turn. A. A has a positive value for the position that's above the axis. What about for the slope? Positive or negative?
Negative.
What about for the second derivative, the concavity? It'd be concave up. What is the question answer about? When does it first become negative? So can A be an answer? No. What about C? Let's talk about each piece. It has a positive value. First derivative. Positive. Second derivative. Could be positive. Could be negative. It looks like it's on that middle value, right?
Yeah.
It could be really close to that point of inflection, so it's possible, right? Which of the points is closest to the point where this becomes negative? So C is looking real nice. Because also farther to the right of C, it's definitely concave down, right? Whereas what's happening at E? One piece of time. It has a positive value still. First derivative. Second derivative. Concave down for sure, right?
Yeah.
But is it the closest to the point where it first?
No.
Let's see.
Yeah.
You gotta kind of logic your way through it. Okay, knowing your terms very well is helpful. This question, it is famous for having one like this on the AP exam where they basically just pick a different function and say, hey, this comes down to the velocity equation. And they do the exact same thing. And you have to reorientate your mind and go, okay, if this is velocity, then the acceleration is the slope. Remember, they're all pretty related. Okay? Yeah. 4. Particle moves on the x-axis at any time t greater than or equals 0. Its velocity is given by the function v of t is equal to t squared ln of t plus 2. What is the acceleration of the particle at time equals 6? Mike says? And?
6.
Beautiful. Let's do it.
T
squared over t plus 2.
2t over.
Right.
So let's agree. This is clearly a calculator question. Wait, it's a calculator question. Oh. Already. But if I was going to do it by hand, I'd have to do the product rule. Okay? So while you're typing in, I'm going to do the product rule and see if I can get the answer as it should be. So, product rule. So I would do left, d right, plus right, d left. So I'm going to write out my pieces. With the ones that are later in the semester, like the LNs, I like writing out the full product rule and plugging everything into it. That way I don't forget something. So it's left, d right, plus right, d left. So left, t squared, d right is 1 over t plus 2, plus right, ln of t plus 2, times 2t. There's my derivative. Now I just plug in 6. So it's 6 squared times 1 over 6 plus 2 plus ln 6 plus 2 times 2 times 6. So 36 over 8 plus ln of 8 times 12. Oop, see? Alternatively, I could have just got a calculator and plugged in that function. Right? I have the ability to take a derivative. Questions. Gotta love questions. The last couple, the last 4, are free response questions. Now there's one, another Riemann sum problem. I'd look at it. Right? Riemann sums are fun. Okay, take the time to look at it. It's not a hard one. And this one, I did check. There is a website that will show the entire worked out. There's a Chegg free one out there that will show this problem worked out as strong as you just take a look at it. It's not hard to do once you know what to do. That's the problem. If you don't know what to do, then this is just a lot of information that looks random. Okay? In any case, if you come across a problem where you're not entirely sure of what to do with it, at least try to fill in some pieces. Okay? When people are asked to grade these, we're asked to look for things very specifically to give points away. We're asked to look for things like, hey, did you at least write down the right units? So literally, you will get 1 point out of 10 on this problem if you write down the right units for every answer. So that's better than 0 out of 10. Okay? Look for those little things to be like, okay, yeah, I may not remember exactly how to do these midpoints, but at least I can take that next step and be like, okay, here are the units right, explain the meaning of the value of the integral. I can do that, okay, in this problem. So there's one. Next one talks about g prime and g. So relating these functions, this is not a velocity or a particle problem. This is just an extra integration question that I wanted to make sure you got to practice on. These last couple ones, the free response ones, there's not very many free response ones that are particle ones, but there are a couple, and so I tried to include a few of them. Try them out. I will post a video on Friday, because we'll probably be asking all of them as much as we can in class. So if you're not here, what I'll be doing.
I'm not going to be here Friday.
So I'll be alone in this room by myself.
Yeah, I'm going to a wedding.
I will try to work through as many of them as I can in the hour that I have, but I will work quickly, okay? So make sure you take a look at the video and see what you like.
I'm still on the
Huh? That is it.
Being able to ask any question about math to someone that knows, or like the person who knows the most about math, or at least one that knows the most knowledgeable math